Hello, so in this video we're going to be talking about the second method which we can use to solve a linear system of a non-homogeneous linear system of ordinary differential equations. The first method, if you remember, involved diagonalization. This method is slightly more algebraic and involves integration, okay, but it's a good thing to have, it's a good thing to practice. And I suppose this is actually more familiar to you if you're used to solving the sort of standard single case, linear system of nth order, or not even a system, an nth order linear ODE, the y double dash plus py dash plus qy kind of thing. Yeah, if you're familiar with solving like this kind of method will be more familiar to you, but there's a lot more calculations involved. Okay, so this is our, it's called variation of parameters, and this is our non-homogeneous system of ODEs, kind of condensed down in the familiar way. Okay, so as usual, what we want to try and do is the general solution, of course, x of t, right, will be based on the complementary solution, so the solution to the non-homogeneous, or the homogeneous parts, in other words, there's no k vector, plus a particular solution which involves kind of the plus k part. Right, so this is kind of just reminding you of what you've seen before. So the homogeneous part will look like this. So it would be dx by dt equals ax. Now I've shown you before that we can form, this is going back to the video, perhaps a couple of videos ago, 2-3 videos ago. I've shown you how to form a fundamental matrix. Okay, a fundamental matrix, and that is just literally a matrix which consists of fundamental solutions. Remember, fundamental solutions is just where all of the solutions are linearly independent, so they cannot be written in terms of any other solution, right? They're kind of fundamental, they can't be broken down any further, and we call that fundamental matrix phi. We give it that notation, phi. Okay, well, fairly obviously, because this matrix here will be a matrix, okay, consists of fundamental solutions, okay, all of those solutions will satisfy this homogeneous case. Yeah, this homogeneous case. So are you happy then that I can just replace x with this fundamental matrix? Whenever I see an x here, at the moment x corresponds to my fundamental solutions. So let's call it, let's say we have a system of equations of two variables. Okay, so dx by dt and dy by dt. So let's say my variables are just x and y. So x corresponds to x and y. Well, now I'm going to have a fundamental matrix which corresponds to those fundamental solutions for x and for y. Okay, so if I just plug that fundamental matrix back into this homogeneous system, all right, then it will still be satisfied. Okay, I can still do that. I've shown you that in the previous, kind of a couple of previous videos. So essentially I can rewrite this as d phi by dt equals a lots of phi. Okay, so I've rewritten this thing now. It's exactly the same thing. It's just now I'm just considering a fundamental solution. I've just put the fundamental solutions back in. Okay. Notice that I can multiply this fundamental matrix by any constant I like. Any constant I like. So let's say this fundamental matrix consists of, I don't know, consists of x1, x2, yeah, and y1, y2, let's say, okay, y1, y2. So this is what my fundamental matrix is going to look like. Yeah, I was a bit confused myself about the notation. I think that notation works. Let's just stick with it for the moment. Okay, well, if I multiply this fundamental matrix by C, so this is my matrix of fundamental solutions, and if I multiply it by C, let's say C1, C2, that's what C is equal to, it's just a vector, and I'm multiplying it by a couple of constants, what am I going to get out? It's going to be C1, x1, plus C2, y1, yeah, plus, what's that, C1, x2, plus C2, y2, yeah, that's going to be my fundamental solution. That's what it's going to equal to, okay? Well, fairly obviously, this is just a linear combination. This is now just a linear combination of my fundamental solutions, right? So it's fairly obviously, if I multiply it by some, if I multiply my fundamental matrix by some constant, it's still going to be a fundamental solution, right? Okay, because the fundamental parts are the x1 and x2, so the x's and y's, right? you know, it's just multiplying those by some constant is fine in this case. So basically, the idea is that I want to say, right, okay, x, you know, x is my solution, similar to what we did for the diagonal case. I'm plugging phi in for x. Okay, so in other words, x is equal to phi. Okay, but I can multiply phi by any value I like. Yeah, I can multiply it by any value I like. So it may not be fundamental anymore. If I multiply it by some constant, it may not be fundamental anymore, but it will still be a solution. You're just multiplying it by a number won't make a difference. It's just the idea of linear combination. You know, this is effectively just a linear combination. Well, a linear combination of solutions is still going to be a solution, right? It may not be fundamental anymore when multiplied by a constant, but it's still going to be a solution. So effectively, this is a solution to my homogeneous part. All right. So the idea is now that I just want to find out what C is. I want to find out what those constants are, and this is where the algebra kind of comes in. So basically, I am looking for, you know, this is my solution. This is, if you like, my complementary solution, my solution for my complementary part. So the solution to my homogeneous part. Yeah, finding the solution to the homogeneous part is actually quite straightforward because you've been through all the thinking before. It's just going to be a linear combination of all your different solutions, right? So these are the linear combination of all my solutions here. Okay, so therefore my solution to my homogeneous part will look like this. So x equals phi, which is my fundamental matrix, but I can multiply it by any constant I like. It'll still be a solution to the homogeneous part. So now what I'm going to do is I'm going to plug it back in, you know, like I did for the case which you're probably familiar with now, just a single ODE. I'm going to now plug this back into my non-homogeneous part to try and find now a particular solution. So I'm going to plug it back in. So x equals phi times c. So I've got d by dt of phi times c. Oops, I'm going to use square brackets there because I'm going to show its derivative of that thing. Is equal to a, lots of phi times c, plus k. All right, so what's this equal to? Right, now, what have I got here? Well, I need to consider what the derivative of phi with respect to t is. With respect to t, so I need to consider what d by dt is. Can I do this, for example? You know, so in other words, does phi depend on t? Or can I just treat phi as a constant? Well, phi consists of all of my fundamental solutions. So I've got x1 of t and x2 of t. So it's literally just a matrix of all of my all of my fundamental solutions. Perhaps I should use the notation which I've been using earlier on this video. So I've got x and y, those are my fundamental solutions, right? And they're both going to be dependent on t. So therefore, if I find the derivative of my fundamental matrix with respect to t, I have to do that. I can't just treat fundamental as the fundamental matrix as a solution, so I can't just stick it out the front. Okay, so effectively, what have I got? This is just a product rule, right? So it's going to be the derivative of phi times my constant vector c. All right, and my constant vector c, of course, will be dependent on time as well. Yeah, plus my fundamental matrix times the derivative of my constant vector c. So that is what this just by the product rule. This is what d by dt of phi times c is. Okay, that's just what I've got written down here. Okay, and that's equal to then the right hand side, which is a phi c plus k. Okay. So that's exactly what I've got there. So what I basically want to do now is I want to find out what C is. Yeah, that's the idea now. I want to try and find out what C is, so then I can try and use that in the particular solution. So let's have a look. What's C? Okay. Well, look what we had earlier on. Let's go right back to the beginning of what we had earlier on. You know, with what we found here. Let's use this. Okay, so I know the derivative of phi with respect to t, so I've written it like this, okay, the derivative of phi with respect to t is equal to a times phi. So in other words, when I've got the derivative of phi, yeah, which is what I've got here, I know that is just a phi, yeah, from what I've just shown you, okay, so that's a phi times c plus phi times the derivative of c, all right, plus a phi times the derivative of c plus k. So that's equals in the middle there. Okay, just doing a little bit of algebraic manipulation. Look, I've got an a phi c here and an a phi c here, so that cancels. So effectively, what it boils down to is phi c dash equals k. Yeah, so phi c dash equals k. All right then. All right. So now because the fundamental matrix is linearly independent, therefore the determinant is not equal to 0. So therefore an inverse does exist. So therefore I can just, multiply through by the inverse of phi and get phi inverse times k. Yeah? And now I just want to find out what c is just by integrating this left-hand side, or this right-hand side. So c is equal to the integral. If the derivative of c is equal to phi inverse times k, then c itself is just going to equal the integral of phi inverse times k with respect to t. Yeah? Okay. So this is what c is equal to. So therefore, knowing that I'm looking for a solution of the form of this, phi times c, that therefore I can just replace c with phi times the integral of phi inverse times k with respect to t. This is what x is equal to, and this is my particular solution. So now my general solution will be my complementary solution, which remember was, so my complementary solution was, this is particular solution. So let's call it actually just xp. Yeah. My general solution x will be equal to my complementary solution plus my particular solution. Exactly the same idea as what we have with an nth order linear ODE. Okay, my complementary solution was phi c, if you remember. Oh, that's awkward. This is complementary. This is a subscript, not my vector here. This little c down here is just a subscript. But I've used c as a constant vector. Okay, perhaps my notation wasn't great there, but this is my constant vector. Okay, plus my particular solution, which is what I've got written up here. So it's phi times the integral of phi inverse k dt. All right. So this is now what my general solution will look like. Okay, which is fine. Okay, that's absolutely fine. Now the thing is, right? Over a definite time, over small systems, either one, so what, let me just talk about now the benefits between diagonalization. I've shown you both methods. First method, if you can remember, was diagonalization, and the second one was variation of parameters, right? Variation of parameters. That was method 1, that was method 2. So, for small systems, either will work well. So either diagonalization or variation of parameters will work well. Okay, there's kind of no reason why you should choose one over the other. So for example, with 2, 3, 4, even 5 variables, either will work relatively well. As soon as you start getting to bigger systems, variation of parameters has a lot more computation involved. And you also have the integration. So it kind of depends whether you have the integration. Whereas with diagonalization, there's kind of less computation involved because you're only considering one matrix as such. But if you look here, integration. Okay, if you're not overly keen on integration, diagonalization will work absolutely fine. But diagonalization, we tend to use diagonalization more if we can kind of recognize a nice matrix. For example, if it's Hermitian, I'll write it out. Okay, which is basically a real and symmetric matrix. Okay, and if you can kind of spot that, then actually it makes things a whole lot easier. And perhaps show you an example in another video of an example where diagonalization is extremely useful. It's far quicker than actually going through variation of parameters. So really, for small systems, which is what you're likely to get in the exam, either method will work well. So it's actually really good to know both methods, because if you're sitting in the exam, one method's not working, then the other method likely will work better. All right.